In this NMR Part 4 video, I'd like to discuss the following. First, I want to go into more detail regarding factors that affect the chemical shift of a signal nucleus. Second, I'd like to say more about carbon-13, NMR, and finally, I want to describe in more detail how NMR signals in an NMR spectrum are actually generated. The chemical shift of a spinning nucleus is due to a number of effects. One of these effects, I've already briefly talked about it, is the presence of electron withdrawing or electron donating groups. An inductive electron withdrawing group lowers the density of the electron cloud about a spinning nucleus, an effect that ultimately shifts the NMR signal of the spinning nucleus to the left, that is, increasing the chemical shift, the delta value of the signal. An inductive electron donating group has an opposite effect, shifting the NMR signal to the right, decreasing the delta value. Now there's another effect. We briefly talked about it before. This effect is due to the presence of pi bonds or an aromatic ring in a molecule. This effect is called magnetic anisotropy. When a molecule has pi electrons in the form of a double, triple bond or aromatic ring, the external field of the NMR spectrum causes a very strong, intense circulation of these pi electrons. This circulation results in a very strong secondary magnetic field that profoundly affects the chemical shift of a nucleus, depending on the location of that nucleus in the secondary magnetic field. Let's illustrate this by examining the chemical shift observed for aromatic protons. Recall that aromatic protons are greatly de-shielded. Their chemical shift is in the range 6 to 9 delta, and that's very far to the left in an NMR spectrum. Here's why. The external magnetic field causes the pi electrons of the ring to circulate in the direction indicated. This circulation of pi electrons generates a strong secondary magnetic field. The secondary magnetic field consists of magnetic field lines that are actually closed loops. Let's look at the direction of the secondary field as we move around a magnetic field line loop. In the center of the ring, note that the direction of the secondary field is down. That is, in a direction opposite to the direction of the applied field. Let's now move around a magnetic field line loop to here where the aromatic proton is located. Notice that the direction of the secondary magnetic field line loop is now up. It's in the same direction as the applied magnetic field. So the net magnetic field that this aromatic proton experiences is the sum, a combination of the external field and the local field created by the magnetic field line. You can see that the net magnetic field has increased, and the increase is great enough it causes a marked de-shielding effect on the signal created by the proton very far towards the left. Alright, let's examine the chemical shift of alkenyl protons. The diagram we're going to see here is actually similar to what we saw before. The external magnetic field will cause the electrons of the pi bond to circulate round and round in the direction indicated here. The circulation creates a secondary magnetic field, a set of magnetic field line loops shown in the diagram. The red arrows show the direction of the magnetic field line loops. If you're right in the center of the double bond, the direction of the secondary field is down, note, in a direction that opposes the applied field. Let's move around the magnetic field line loop to where the alkenyl proton is located, And you can see that the direction of the secondary field line is up and in the same direction as the applied magnetic field.
So the net magnetic field felt by this hydrogen has increased. It is greater than the applied magnetic field alone.
And the increase is sufficient to cause significant de-shielding of the signal created by this hydrogen. Now the de-shielding is not as great as the aromatic proton. The aromatic proton had a delta of 6 to 9. Here, most cases it falls between delta 5 and 6. Let's now look at the chemical shift of alkynyl protons. It is a proton attached to a CC triple bond. The magnetic field, the external magnetic field, is shown here, pointed up. This will cause the triple bond electrons to circulate in the direction indicated here. The triple bond acts like a kind of cylinder, and its pi electrons travel around and around that cylinder, and as they do, they will generate a secondary magnetic field, secondary magnetic field line loops shown in the diagram. Let's look at the direction of the secondary field line loops as before. Well, if we're, say, right in the middle of the triple bond going down the CC bond axis, the direction of the secondary field line is down. It's opposed to the direction of the applied field. Note that where that hydrogen is located, that the secondary magnetic field lines through it are pointed down, so that the net magnetic field experienced by this alkynyl hydrogen is the difference between the secondary field line and the applied external field. That is, it's going to be decreased. The magnetic field experienced by this hydrogen will be lessened, and the effect of that is to cause magnetic shielding of this hydrogen. It's going to cause the chemical shift to be pushed towards the right. And typically, you see a range from 1.7 delta to 2.7 delta. I now want to discuss carbon-13 NMR. C13 NMR is similar to proton NMR, but there are some important practical differences. The C13 nucleus is like the proton, the H1 nucleus, in that its magnetic quantum number I is 1/2. This means that, like a proton, C13 nucleus spins in two possible directions, and consequently it produces NMR signals analogous to proton NMR signals. However, one difference between C13 and H1 is the relative number of C13 nuclei in an organic molecule compared to the number of H1 nuclei in the molecule. H1 is the most abundant isotope of hydrogen. Its abundance is more than 99.9%. Means that almost every proton in an organic molecule is an H1 atom. In contrast, the percent abundance of C13 is very low, only 1%. That means that only 1 out of every 100 carbon atoms in an organic molecule is C13. 99%, 99 out of 100, are C12. But C12 is magnetically inactive and does not produce an NMR signal. So consequently, when one does a C13 NMR spectrum of an organic compound, assuming that one is using the natural abundance of the C13, it's much harder to see the C13 signals in the NMR because there are so few C13 atoms. But modern NMR instruments are so sensitive they actually can see the low abundance of C13 nuclei. And also this, when one does a C13 NMR spectrum of a compound, one follows this procedure. Numerous repetitive scans are carried out on the order of 50 or 100. The average of these scans is recorded, and the average scan tends to cancel out random noise signals, leaving behind the observable C13 signals. So it's easier then to see those small C13 signals if one removes the noise peaks that would normally accompany them. Noise peaks can be about the same size as the C13 signal peaks. Now there's another issue with C13 NMR. A carbon atom in a molecule is typically bonded to hydrogens, 1, 2, or 3. A methyl group is bonded to 3 hydrogens, methylene bonded to 2, and so forth. Now remember that each proton has an I of 1/2, and that means then that protons that are bonded directly to a C13 atom are going to cause spin-spin splitting of the carbon 13 NMR signal. And as a result, the C13 NMR can become very complicated and more difficult to interpret. But modern NMR technology has found a solution to this. The NMR spectrometer uses what's called an H1 decoupler. An H1 decoupler is an adjustable radio frequency generator, and when used, it will remove the coupling effects of the protons that are directly bonded to a C13 atom. As a result, one observes sharp, single, unsplit signals for the C13 atoms. Look at the next slide for an example. The spectrum here at the top is a C13 spectrum without the proton decoupling. So what you're seeing here is a signal due to each carbon, but each carbon split into a multiplet by the hydrogens directly bonded to it. And as a result, the spectrum is rather complicated looking. Now, for example, this methyl group, the C13 of the methyl group, its signal is actually split by the 3 neighboring hydrogens that are directly bonded to it. Remember the n+1 rule. The C13 signal is split into a quartet right here. Well, in the spectrum below that, H1 decoupling has been carried out. So the coupling effects of the hydrogens directly attached to carbons are completely removed. As a result, for each carbon in the molecule, we just see a single sharp signal. The spectrum here is much, much simpler and therefore easier to interpret. In this slide, we show a chart of carbon-13 chemical shifts. And if you compare and contrast with other charts that we've shown for the proton chemical shifts, you notice here that one obvious difference is the range of delta values for C13. The range for C13 is much broader than for proton. Typically for C13 runs from 0 to over 200, say 250 parts per million, whereas for the proton the range runs from 0 to around 12, generally most commonly between 0 and 8. So for C13 the range, the ppm range, is much broader. In this chart, one thing that it points out is you're going to see the same kind of chemical shift effects that we saw for proton. You see the effects of inductive electron withdrawing and donating groups, and you also see the effects of magnetic anisotropy. It is the effects of the pi electrons of double, triple bonds and aromatic rings. And for example, C13s that are of a hydrocarbon that aren't attached to electron withdrawing groups tend to have a lower delta value here. And when you start attaching electronegative groups like oxygen or halogens, that causes the chemical shift to the left, increasing the delta value. The carbon 13 of a triple bond, there's actually two effects. There's the effects of the circulating pi electrons and the inductive effect due to the sp hybridization state. And anyway, on average, the chemical shift comes out around 80 or so. So the carbons of an alkene or aromatic ring, the magnetic anisotropy effects really do come into play. The circulating pi electrons cause significant deshielding, shifting those carbon signals more to the left with delta values around 120, 130, 140 or so. Here is a carbonyl carbon. There is the effects due to the circulating pi electrons and also the inductive withdrawing effect of the oxygen, and as a result the chemical shift is very, very, very large, greater than 150. Here we show a C13 NMR spectrum for 1-propanol. In this spectrum we have carried out H1 decoupling. So all the splitting effects of the hydrogens directly bonded to carbons are completely removed. Well, there are 3 carbons in a molecule. Therefore we would expect to see 3 signals. Each carbon is different from the others. Each carbon is a set of one non-equivalent carbon, if you will. And so because there are 3 different carbons, we see 3 different signals, and here they are, 1, 2, 3. Now, interestingly, in this one, you would normally see a TMS. For some reason it's not showing here in this example, but normally you'd see a peak right here for the TMS standard. That is, the C13s of NMR would show up as a signal which would be set at 0, just like was done for proton NMR. The solvent that's typically used in C13 is deuterochloroform. Now, because decoupling has been removed, again you see 3 narrow sharp singlets for each carbon. You also note the chemical shift effect. The hydroxyl oxygen is electronegative and is going to be pulling electrons away from all the carbon atoms. The closer a carbon atom is to the electron withdrawing oxygen, the more its electron density is lowered, the greater the chemical shift effect, the greater the deshielding. So this CH2 carbon, labeled C, being directly attached to the oxygen, we would expect that to be the leftmost peak. And here it is. The signal right here is due to the methylene directly attached to the hydroxyl oxygen. Now the methylene B, however, being farther away from the electron withdrawing oxygen, has a little higher electron density, and the chemical shift is not as great. It has a larger delta value. This signal here is due to the methylene labeled B. The methyl is the carbon that's furthest away from the electron withdrawing oxygen. Its electron density, the electron density of the electron cloud about it would be greatest. Would therefore have the least deshielding, the most shielding of all the carbons, and would have a signal that is the furthest to the right, the less deshielded signal. So this signal here, labeled A, is due to the methyl group. All right, now there's something else. With proton NMR, we learned that the number of protons in an equivalent set are related to the size of the peak that that set produces. The more protons there are in the set, the larger the peak. However, when proton decoupling is carried out in C13, as it normally is, something interesting happens. There's a phenomenon called the nuclear Oberhauser effect. And because of this effect, we actually lose information. There turns out to be no longer a relationship between the number of carbons in an equivalent set and the size of the signal. Now, if that effect didn't occur, if this was just like the proton NMR, because there is 3 carbons and 3 signals, and there's 1 carbon A, 1 carbon B, 1 carbon C, because they're all equal, it is 1, 1, and 1, we would see 3 singlets that are all the same size. But when decoupling is carried out, that information is no longer retained. And it turns out there's no longer a relationship between peak size and the number of carbons producing that signal. Instead of seeing 3 equal size peaks for this sample, they have different sizes. And the sizes can really vary all over the place. They could be small, medium size, or large. One just has to accept that. And as a result then, when one does a C13 NMR, you do not carry out peak integration because it wouldn't give you any information. And one has to just accept the fact that peak size no longer has a relationship between the number of carbons producing it. That information becomes lost because the decoupling is carried out. Alright, let me explain how an NMR spectrum is actually created. The sample is placed in a powerful magnetic field. The nuclei of the atoms of the molecules precess about the magnetic field. Some are aligned with the field and some against the field. Remember, the against field alignment is the higher energy state. A powerful RF pulse is next delivered to the precessing nuclei. This causes essentially all of the spinning nuclei to be excited, to basically flip to the higher energy state. Now, at the end of the RF pulse, the excited nuclei begin losing their energy to return to their original state. This process is called relaxation. As the excited nuclei relax, they emit energy in the form of RF radiation. Each relaxing nucleus emits RF radiation of a specific frequency. Now, the NMR spectrometer records the combined radiation signals of all the relaxing nuclei over time. This over time combined radiation signal is called the free induction decay, or FID, signal. Alright, the next thing that happens is the computer takes the FID data and mathematically converts it to an NMR spectrum. It does this by conducting a mathematical algorithm called a Fourier transform. Specific data points from the FID signal are selected. The Fourier transform algorithm acts on those data points and converts it to an NMR spectrum.